Welcome to our focused explainer on lab practical micromeasurements. Today, we're taking those incredibly dense, kind of dry manual instructions from your Class 11th physics notes and totally transforming them. We're turning them into a clear, straightforward survival guide for your lab. So, if you've ever stared down at a heavy metal instrument covered in tiny, confusing lines and just wondered, how on earth do I even read this thing? Well, you are definitely in the right place. Let's get into it.
Let's dive right in with a super practical question. How do you actually measure something that is way smaller than a single millimeter? I mean, think about it. Standard rulers really only give us markings down to 1 millimeter. But consider this. A standard human hair is about 0.07 millimeters thick. It literally just vanishes between the lines of a standard scale. You can't even see it on a regular ruler. So we need instruments specifically designed to conquer these microscopic spaces.
And that brings us to the first real hero of our lab guide. Check out the really ingenious design of the Vernier calipers, named after its inventor Pierre Vernier, by the way. As you can see, you gently place a spherical body right between the fixed jaw on the left and the movable jaw on the right. But the real magic happens along the arm of the tool, where two totally distinct scales are working together.
The absolute brilliance of this instrument lies in how it splits the work. It combines a standard, gross measurement with a super precise, fine measurement. Your main scale is giving you that gross, baseline reading in millimeters, just like a normal ruler. But then, the sliding Vernier scale acts almost like a mechanical magnifier. It allows you to read those highly precise fractional measurements that fall right into the empty spaces between the main scale lines.
Okay, so what does this actually mean for us? The crucial point is understanding exactly how much precision this tool gives us. We call this the Vernier constant, or more commonly, the least count. In a standard lab caliper, 10 divisions on that little Vernier scale equal exactly 9 divisions on the main scale. Because of how that math works out, the least count becomes exactly 0.1 millimeters. That tiny fraction right there, that is our fine-tuning power.
Right, so how do we actually use this without getting totally lost in the math? It's actually a pretty foolproof 4-step formula. First, you just note the main scale reading just before the sliding scale 0. Simple enough. Second, you look closely and find the exact Vernier division that perfectly aligns with any line above it. Third, you multiply that specific division by our least count. And finally, you just add that tiny little fraction to your main reading. Boom, total reading.
Now, when you're physically in the lab logging this data, keeping your main scale, Vernier scale, and total readings perfectly organized in a table like this is absolutely key. But you might be wondering, why take 3 readings instead of just 1? Well, guidelines specify that to get an accurate mean diameter, you always need to repeat measurements in different perpendicular directions. This accounts for any slight, invisible irregularities on the object. Because let's be real, a true scientist never relies on just a single data point.
But wait, what if we need to level up? What if we have to escalate our precision for something even smaller, like a really thin metallic wire? Honestly, the Vernier calipers simply aren't going to cut it. Enter the rotational mechanics of the screw gauge. Instead of sliding jaws, we're placing our delicate wire between a fixed stud and a central screw. We've officially moved from linear sliding to rotational threading to achieve some pretty extreme precision.
The whole operation of this new tool boils down to one single concept: its pitch. The pitch is literally just the linear distance the screw moves along the main scale in one complete rotation of the cap. So if 4 full rotations move the screw exactly 4 millimeters, your pitch is exactly 1 millimeter. 1 full turn equals 1 millimeter forward. Makes sense, right?
So, to find the least count of our screw gauge, we just take that pitch we just found and divide it by the total number of divisions engraved horizontally right there on the thimble. If our pitch is 1 millimeter, and we divide that by the 100 tiny divisions on the dial, we get a least count of 0.01 millimeters. Guys, we are now literally measuring down to 1,000th of a centimeter. That's incredible.
Now, pay attention to this part because it's absolutely critical when you're handling the instrument. When placing your wire lengthwise, you must, and I mean must, move the face using the little ratchet head at the very end of the tool, and you stop the exact second it clicks. Never, ever twist the main cap tightly. If you force it, this mechanical screw will just squash that thin wire right out of shape, completely ruining your data. And yeah, probably your lab grade too.
Just like our Vernier calipers earlier, taking the actual reading here is a pretty simple combination of the 2 scales. First, you note the linear scale reading that's visible right at the edge of the cap. Then, you find the circular reading that is perfectly overlapping the central reference line. You multiply that number by our incredibly small least count, and then just add the 2 together to reveal the exact diameter. Easy!
Okay, pause. Before you go finalizing any of your data, you have to defeat the natural enemies of precision measurement. First up is zero error. That's just when your scales happen to misalign when the tool is completely at rest. Second is backlash error. This one is caused by mechanical friction and play within the screw's threads. Think of it like a steering wheel that has a little bit of give before the car actually starts to turn. If you rotate the screw back and forth, that internal looseness means it won't immediately move forward when you reverse direction.
Thankfully, you can actually correct these issues. Mathematically, you just apply a zero correction to your final numbers. Physically, you just have to adopt some really strict handling precautions. Mechanically speaking, always use the ratchet and turn the screw in one uniform direction, no back and forth, to completely prevent that backlash we talked about. Visually, make sure you look completely straight on to avoid any parallax error. And finally, measure the wire at 5 equally spaced places to account for any real-world imperfections in the metal.
So as we wrap up this explainer and you get ready to head into your Class 11th lab to master these scales, I really want to leave you with this final thought. We've just seen how these totally ingenious, entirely mechanical designs allow us to measure down to 1/1000th of a centimeter, literally just using our bare hands. So how might these brilliant historical principles of micromeasurement have paved the way for the crazy, laser-precise tools we use today in modern nanotechnology? It's pretty wild to think about. Good luck in the lab.